As we have seen in previous videos, natural numbers, integers, and rational numbers are quite intuitive. But once we start looking at numbers like the square of 2 and pi, we start pushing our minds to the limit. Many people first got exposed to these numbers when they started learning the Pythagorean theorem and the circumference of a circle, and they saw for the very first time numbers that are not rational. Very often, these numbers are presented as infinite decimals. For example, the square of 2 starts with 1.414 and so on, and pi is 3.14159 and so on. But we are all finite beings. How could we possibly work with numbers that have infinitely many digits? Well, the short answer is we don't. And this is accomplished through an ingenious idea: finite approximations with arbitrary precision. Let's take a closer look of the square of 2 and see what we can do. The ancient Greeks knew how to construct this number as a length. What you do is you take a right-angled triangle whose height and base are both 1. Then the hypotenuse is going to be the square of 2. As a result, the square of 2 is indeed a real quantity. But how large is it exactly? Well, why don't we ask the following instead? What is the best approximation to the square of 2 from below, having at most n digits after the decimal point? If n is 1, it will be 1.4 because 1.4 squared is 1.96, whereas 1.5 squared is 2.25, which is larger than 2. What about when n is 2? Well, it will be 1.41 because 1.41 squared is 1.9881, whereas 1.42 squared is equal to 2.0164. From the point of view of the number line, we can get closer and closer to the square root of 2 as we ask the question with larger and larger n. So this is the number line, and let's draw square root of 2. So this length is square root of 2, and if we draw a circle centered at 0 with radius root 2, it will look something like this. And to get the first digit, you chop up this interval between 1 and 2 into 10 pieces. Obviously, I haven't done a very good job drawing this. And what you notice is the square root of 2 is more than 4/10 larger than 1. And to get the second digit, what you do is you chop up this interval here between 1.4 and 1.5 into 10 pieces, and you'll notice that it is just over 1/10 of this interval from 1.4, and so on. So if you manage to do this repeatedly, you'll get an approximation of square root of 2 with as many digits as you like. In general, if you can pinpoint exactly where a real number is on the number line, you can use this method to get an approximation with n digits after the decimal point, and its value is less than 10 to the minus n away from the real number. The digits that we obtain this way are called the decimal expansion of the number to the nth decimal place. And in practice, computations with real numbers are often done approximately with a fixed precision. But if you are not carrying out actual computations, you can simply think of pi equals to 3.14159 as a way of saying this. You tell me how many digits of pi you want, and I'll give you its decimal expansion with the required number of digits. Notice that this is no longer an infinite problem. We can do this in finite time, and indeed, there are formulas for pi that allow you to compute pi to as many digits as you need. So, given this way of thinking, how does one know if two infinite decimals are equal? For example, given two numbers, a and b, where a, written as an infinite decimal, has the following digits. So one digit before the decimal point, called a0, and a subscript minus 1, a subscript minus 2, a subscript minus 3, and so on. And the kth digit after the decimal point is a subscript minus k, and so on, goes on forever. And b is given by this. How do we know if these two numbers are equal? There are infinitely many digits. It is very tempting to say that a equals to b if and only if ak is equal to bk for all k. It is a very reasonable definition for equality, because if two numbers have the same digits, they must be equal. But here is where things get interesting. What about the number 0.99999 and so on, and 1.000 and so on? Most of us have been taught that they both represent the number 1, and we will probably agree that they should be the same number. But it doesn't fall into our definition of equality presented here. So do we include this as an exception? Is there a way to include this case as well as the case when the digits are all equal? It turns out that there is a way to formulate equality of two infinite decimals, unifying both cases. We say that a and b, as given by these two infinite decimals, are equal if no matter what positive value epsilon you give me, I can give you a natural number n big enough so that if we take the decimal expansions of the two numbers to n decimal places or more, they differ by less than epsilon. This is quite a mouthful, so let me repeat this. So we say that a and b, as given by these two infinite decimals, are equal if no matter what positive value epsilon you choose, I can find an n big enough so that if you take n or more decimal digits from the two numbers, then the resulting approximations differ by less than epsilon. In casual terms, what this is saying is, if the gap between the two numbers is smaller than any positive size that you pick, we regard the two numbers as equal. At first hearing, this sounds a bit like cheating, but it works because what non-negative quantity could possibly be less than any positive quantity, no matter how small it is? Having said this, some people do work with numbers called infinitesimals, but these things are way beyond the scope of what we are doing here. Now, clearly, if all the digits are the same, then this definition will definitely regard them as equal. But what about 0.99999 and 1.00000? The thing is, if you take n decimal places from 0.99999, the difference is going to be 10 to the minus n. So as n gets larger, the difference gets smaller. And it can be smaller than any positive value that you pick. And so, according to this definition, 0.99999 is the same as 1.00000. We can also extend this idea to say that an infinite decimal is equal to another number in the following manner. We say that this infinite decimal, given by the digits ak minus 1 down to a0 before the decimal point, and a minus 1, a minus 2, a minus 3, and so on, equal to some number b, if no matter what positive epsilon you give me, I can give you a natural number n such that if you take this approximation, where little n is bigger than n, is going to differ from b by less than epsilon. And using this definition, one can show that 1 over 3 is equal to 0.33333 and so on. Because if epsilon is really, really small, say 1 over a million, I can go far enough here so that 1 over 3 minus that approximation is less than this epsilon value. And this is how we can compare fractions against infinite decimals. Now to end, I would like to recommend a book for further reading. The title of the book is simply Calculus, and the author is Michael Spivak. This is the calculus textbook that my first year calculus course used. The course was a great course, and it was taught by a great professor, Brian Forrest. And if you have a chance to be taught by him, you're lucky. I have to say that this textbook is the only textbook of any subject that I enjoyed reading during my university years. It takes a rigorous approach to calculus, but in an engaging way. It was simply a pleasure to read the insights and motivations behind the theorems and definitions. It has an appendix that contains a fairly good treatment of the real numbers. It does require some mathematical maturity to get through, but I believe working through it is well worth your time and effort, especially if you have never learned how the reals are constructed.